All right, welcome. This is September 17th, 2014, and this is the second class on part 4 of Kepler's New Astronomy. And we're going to be talking about chapters 45 through 50 today. This is probably about the most intense group of chapters, and trying to do them in a week it's almost insane. But we'll get an overview on that today. Just to give a recap of the book so far, which I want to start every class by doing, just to keep things in memory. For starting just with what we've done in part 4. Well, let's go back to the beginning. Since before the New Astronomy. So in the Mysterium Cosmographicum, Kepler tried to figure out why there were 6 planets, why they had the distances they did. He had a hypothesis of Pythagorean diplatonic solids lying in between the different planetary orbits to give their spaces. He wasn't really certain, though, about the sizes of the planetary orbits, because what he was using, Copernicus or Tycho Brahe's, what they had put together, was based on using this mean sun. So part 1 of the New Astronomy is Kepler saying, let's make it very clear that using the actual sun for our orbits, instead of having the planets go around the mean sun, and I really don't mind going over what that difference is again in the Q&A if there's still questions on it. So part 1, he says using the real sun is definitely different. It's provable which one's right or which one's wrong based on looking at the observations it would predict. That's part 1. Part 2, he says, okay, I'm going to go back and I'm going to redo Mars's orbit. I'm going to use the assumptions of the ancients, meaning Ptolemy and Copernicus and Brahe, who maybe didn't appreciate being called ancient, but anyway. He says he's going to use their technique with the actual sun as the basis of Mars's orbit. He assumes that Mars moves in a circle, that it has an equant. He creates a vicarious hypothesis that works fantastically. The vicarious hypothesis itself is really 4 things. It's the distance from the sun to the planetary center. It's the distance from that to the equant. It's the orientation of all of that, the line of apsides, and it's adjusting the equant. The equant's like a clock, and you have to figure out how fast it goes. You also have to figure out how to set it. So those are the 4 things. Those are the 4 things that make up the vicarious hypothesis. The distance in the vicarious hypothesis from the sun to the center of Mars's orbit is suspicious. Kepler shows without a doubt that it's not right, and that if he adjusts that distance to be in line with what observations say that distance has to be, then it doesn't give the planetary location correctly anymore. It's 8 minutes off. Kepler sets Mars aside. In part 3, he looks at the Earth, and he shows that the Earth has an equant in its orbit. He doesn't really believe in equants, but the point is that he shows that the Earth changes its speed. Since he's shown that the Earth changes its speed, that means that he can say, now I can continue with my universal physical hypothesis that there's a power in the sun that moves the planets. See, the Earth changes its speed too, even though Copernicus didn't think it did. Kepler showed yes, it does. And now he can start trying to explain all the motions physically, and that's where he's at the beginning of part 4. He's, the bus dropped him off. He's here in this new area. He's in this new spot. He's got a physical power of the sun that moves the planet around the sun. And in the beginning of part 4, in what we did 2 weeks ago in the last class, Kepler shows that Mars does not move in a circle. Definitely doesn't move in a circle. That for both the reasons of the distances, that it's closer at the quadrants than a circle would suggest, and when it's made to move in a circle, it goes too slowly on the sides, meaning that if it were brought in, that would speed it up because it would be closer to the sun. So for those 2 reasons, he had concluded in chapter 44, Mars doesn't move in a circle. You got to squeeze it in like a sausage. So where we are now with this group of chapters is we're going to look at Kepler's first hypothesis of trying out, well, how does it move? So looking over the assignment here, it said read the chapter summary and the whole chapter for 45. So we're not going to read the whole chapter together here, but let's take a look at what his main hypothesis was. He says that some of the problems of chapter 39, which made it. Let's go back to that first. So in chapter 39, Kepler had said that he showed how hard it would be for Mars to move in a circle. He said, if you want Mars to, go around the sun, changing its speed, and also get further and closer so that it traces out a circle. Here, the dashed circle is centered on the sun, and the solid circle is, it's just a circle. It's going around that other point. Kepler puts this epicycle, and he shows that if you wanted Mars to keep changing how far away it was to make a circle, it has to move in a really unusual way. Differently at the different parts of the circle, and he says it's too hard, it's too much, it's just not possible. So what he does in chapter 45 is he says, well, I'll tell you what, how about I'll have Mars move. Let me turn the screen sharing on. If you want to look at the screen, just make sure to choose that view. So here's Kepler's idea. He says, okay, I'll have Mars. So we've got, it's going off the screen, but that's okay. Well, there we go. Now this epicycle here is now going to move at a constant rate. We just watch it. If you watch the, say that the gamma is noon. So we've got 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The epicycle twists uniformly. Because the planet's moving slow in this region of its orbit, but the epicycle's going at its full speed, the planet ends up getting pulled inwards, which, as the planet speeds up towards perihelion, it catches up with the epicycle having gotten ahead of itself, and that brings it, it catches everything up by perihelion. So that's Kepler's idea, and he's about to, he says maybe he should have known better. He says, what they say in the proverb, a hasty dog bears blind pups, happened to me. And he feels that he's being a hasty dog, and he's about to bear some blind pups. But that's what he's going to try out. So there's his hypothesis for the next 5 chapters. So I'll go through each of these, and then I would like to, again, like before, have a lot of time for discussion and questions. Because, the stuff's in the, it's in the book and on the web pages, so I feel like discussion's better than teaching, per se. Then there's a trouble that comes up with this. One of them is that, let me see if there's a good picture on here I'm thinking of. One of the troubles that Kepler has is that this, the new circle that he draws, this new, he draws a, like an orbit for the planet. He says, as it's gone from delta to epsilon, that would be its correct distance. Alpha epsilon is the correct distance of the planet based on the epicycle, but it would have actually gone slower and be back here at mu. And he's got to figure out how that would happen. Unfortunately, because the twisting of the epicycle changes the planet's longitude, changes its position, and because the changing position changes how fast the planet moves around, the two things, you can't separate the two, as he's thinking about it here. He's got the speed going around changing, and then the epicycle is acting on top of that, and there's no real way of separating the two. He also has a specific problem that comes from why he can't add up the distances anymore, and that's in the aside on chapter 46. Let's take a look at that together. Let's look at this problem. Where is it here? Here it is. So let's go over what he's looking at. So just to talk about the contrast between this chapter in chapter 33, in the past, Kepler divided the orbit evenly. And you would say the time it took to move each 1 degree was how far you were from the sun. That would be the time it took to move that distance. What he's done now, though, is he's drawn a circle where the positions on the circle correspond to the right distance from the sun at a certain time. So moving around the circle is evenly spaced amounts of time, not distance anymore. This means that you can't add up all of the distances to get the total time. Here's why. Let's read through this aside. So it says, to help further, pose this question to yourself. Let's say you're able to walk at a pace of 30 minutes per mile, or jog at a pace of 10 minutes per mile. What would be the average pace under the following 2 scenarios? So the reason of thinking of a pace rather than a speed is this is more in keeping with Kepler. Kepler would say to move a certain amount on the eccentric, the time it takes is based on how far you are from the sun. So in order to move 1 mile, how many minutes does it take? So that's the Keplerian way of talking about it. So the first example is that we walk for 2 miles and then we run for 2 miles. What's our average pace? So to figure that out, a pace is an amount of time per distance. We know the total distance is 4 miles. We walked 2 of them, we ran 2 of them. How long did it take to walk 2 miles?
Took you an hour?
Right, it took an hour. And then how long did it take to run 2 miles?
20 minutes.
Right. So overall it took us 80 minutes to go 4 miles. So the average rate, 80 minutes for 4 miles, that comes down to 20 minutes for 1 mile. So our average pace was the average of the walking and the running paces. The average of 30 and 10 is 20. Okay. Now let's take the other one. We walk for 60 minutes, and then we run for 60 minutes. Now our average pace is how many? Let's take a look. So if we walk for 60 minutes, how far did we walk?
Uh, 2 miles?
Yep. And then if we ran for 60 minutes, how far did we run?
6 miles.
So a total of then 2 miles plus a total of 8 miles. So it took us 120 minutes to go 8 miles. So what's our average rate per mile then? The total time was 120 minutes. The total miles was 8. So 120 minutes for 8 miles means how many minutes for 1 mile?
You want to say, Doug?
I gave you the answer. I don't know if it's the answer though.
Okay, well, Doug says 15.
Yeah, 15's right. So in the so the first one, the average rate was 20 minutes a mile. In the second one, it was 15. So, you know, in both cases, it seems like you've got the same amount of 2 speeds. One's 30 minutes a mile and one's 10 minutes a mile. When we did each one for the same amount of distance, the average was the average you'd expect, 20 minutes per mile. When we did them both for the same amount of time, the average wasn't 20, it was 15. So because of what Kepler's doing in this chapter, since he's dividing up the orbit not by equal amounts of distance, but by equal amounts of time, if he's got the rate, you know, how long it takes to move for each of these spots, but he knows them for equal amounts of time, it's like the second example, where we walk for 60 minutes, then we run for 60 minutes. So if you try to add up the 2 things, in the first case, we can add 30 and 10. We get 40. We divide it in half. We get 20. That's the average in the first case, is 20. In the second one, the average came out to be 15. Since the first case was like chapter 40, where he used area to measure the total time, because he kept adding up distances to parts along the orbit. That kept telling how long it took to move 1 degree. You add up all those distances, you get the total time to move, 40 degrees. Not anymore. Now, because Kepler's dividing the orbit by time, to use this epicycle thing, he can't use area anymore. So in these coming chapters, he's not going to be able to use area or anything geometrical to measure the time. He's going to have to divide the orbit up into 360 degrees, or really 180, because he just does half of it, and then the two halves are the same. He divides it up into 180 degrees, and he's got to calculate out every single degree one at a time. And if he's going to do it the fully right way, he can't take any shortcuts. So this is a really major, that's a big downer. That's a real problem here. And he's later going to say, I can't imagine that God would have done something so ungeometrical. But for now, he's giving it a shot. So in chapter 46, he's trying to figure out, how he can, figure out how long it takes the planet. Let me draw something over on the paper over here. Switch your view to that, because I think that'll help make something clearer here. Just to show what his problem is here. Okay, so so when he's the reason. Remember, he's working off of an epicycle that he says is rotating at a constant speed. And that epicycle is always the same distance from the sun. I mean from the sun. So let's say Mars is up here. By the time the epicycle's over here at 90 degrees, by the time the epicycle's down here, just to sketch out what his hypothesis is in this chapter. Over here, after the planets move 90 degrees of distance, the epicycle would have moved more than 90 degrees. It would be over here. I'm sorry, I didn't draw that right. Right, the whole thing's tilting this way. So Mars, it would have been over here, but it moved more than 90 degrees past it, and it's actually right here. By the time we get down to the bottom, the epicycle is now twisted from where it started, on the outside. It's now twisted 180 degrees, putting Mars right here. We tilt the whole thing this way. Mars would be here on the inner part. But the epicycle is twisted. It hasn't been able to move a full 90 degrees because the planet moves fast down here. So in less than 90 degrees of time, the planet moved 90 degrees of distance. And so now here's Mars. So overall, we're getting an orbit where Mars is coming in on the sides. This is what the circular orbit would have been. Mars would have always been pointing up on the epicycle. That would have been a circle. Instead, he's got this hypothesis in chapter 45 that makes Mars come in a little bit. So what he does is he says, well, I don't know where Mars is at any particular time, but I do at least know how far away it is. So what he does is he takes just one portion of his diagram. He just takes the sun over here to the epicycle, and he just watches as Mars moves along the epicycle, all these different spots along it. How far are each of those spots from the sun? And he says, well, this is equivalent. He's got this drawing that looks something like this in the book. He says that's equivalent. Those distances are all equivalent to if I had just taken the size of the epicycle, put it in the center of my orbit, and then put the sun right here. So that this distance would be the same as this long distance here. This short distance, perihelion, that would be the same as this short distance. It's like going all the way to the center and then coming back the size of the radius. All the way to the center, coming back the size of the epicycle. Same thing. Going over here to 90 degrees. Same thing as heading right over here. Because so you just transpose it. Any of these spots that you would go to on the epicycle, you just figure out where would I stick that spot. Oh, there we go. So he converts all of the possible distances of the planet. He turns them into this. So he says, here's our aphelial distance, here's the perihelial distance, and if we move evenly along this, he calls it the fictitious semicircle. He only uses 1/2 of it. That's why he calls it a semicircle. Along this fictitious semicircle, this isn't the orbit of the planet. All he's using it for is so that these distances keep giving us the distance of the planet at this angle of time. Right, so here's another spot where you'd say, here's the distance of the planet after this amount of time. So that's why he has that problem we just talked about, because you're now not looking at equal and minus along the orbit. He's using this handy thing to say, well, I don't know where the planet is, but I always know its distance. And he says, well, but if I'm adding them up by equal amounts of time, it's like that problem of averaging your overall speed. If you walk and run for 2 miles, your average speed is the average of your walking and running speeds. If you walk and run for an hour each, like on this fictitious semicircle, each degree means a certain amount of time, then you can't just add them up and take the average. So he's got to do it degree by degree, and he says that that's really going to make things tough. In fact, in this chapter, he can't do it. He says, you know what? In chapter 46, there's so many troubles in trying to figure out where Mars will be that he actually does just give up, and he says that he's going to use the vicarious hypothesis. Let's switch that to the screen sharing for those of you watching on there. Let's take a look at that. So what he does on the diagram you see here, he's there we go. He's cheating a little bit and using the vicarious hypothesis here. So what he's got, so that's a lot of points, isn't it? Let me pause it. Oops, that didn't pause it. There we go. I'm going to point this on the screen. Hopefully you can see it. It's a little unclear. So Kepler draws this this gray circle. That's the fictitious semicircle. So that's the circle. It's centered on B. At this time, that's where the planet would see. That's the right distance of the planet. Kepler then uses the vicarious hypothesis to get the direction the planet would be in, and he says, well, let's just make it at that direction, but we'll use this distance. He's not doing this to have a specific answer or anything. He's just doing it to get a bit of a look at what shape the orbit would be. And you can see it looks like an egg. If we exaggerate it a little bit, hopefully you can see that it's definitely narrower at the bottom than at the top. So it looks eggish. He said he doesn't know what shape this is yet, but he says it's definitely not an ellipse, some kind of egg. So obviously using the vicarious hypothesis is no good. In chapter 47, this is really interesting. Kepler says, well, gosh, the planet does not move in an ellipse, but it seems pretty close to an ellipse. What if I use an ellipse to approximate it? So he gives it a shot. He figures out about how far in it should come in at the side, And there's a very important number here, which is in your homework. This is the answer. So if you didn't do it, now you know what the answer is. 858. 858 is the width of the lunule. That's the width right here. So 858 is the amount that Kepler says he's going to try bringing the planet in on an ellipse. And then he can use equal areas, equal times to measure the speed of the planet, to make it move along there, to make Mars move along it. Which he does. It's very, very conveniently here's the picture. Let me take a look on there. So in this picture that you can see, if you want to figure out how much area has been swept out on the ellipse in green, it's proportional to the area swept out on the circle in red. So Kepler's saying, let's say the planet moves in an ellipse, even though it doesn't. Here's their ellipse. Well, how much area did it sweep out when it moved to here? That area is proportional to this red area swept out on the circle. And that he's done. He's done that in chapter 40. He's done that in chapter 43. So in chapter 47, he applies area time to measure out where would the planet be on an ellipse. And this is what he gets. There's his ellipse. Let's take a look at that. So that's the ellipse of chapter 47. It's not the ellipse that the planet actually moves on, and Kepler knows that because these are the numbers that he gets are wrong. Take a look at these numbers. You can see them. They're on the website. I get at let's say at 45 degrees, for example. The vicarious hypothesis says 4120. Using the circle with area time gave us 4128. Right? The circle is too far ahead at that octant. Using area time with this ellipse, it's 4114. Too slow by the time it's reached the octant. At 90 degrees, it's fine. The circle's off by 24 seconds. This ellipse is off by, 2.5 minutes. Not too bad. At 135 degrees, at the lower octant, the circle is too slow by about 7.5 minutes. The circle moved too slow in the middle longitudes. The ellipse is too far ahead by 7 minutes. I'm going to go ahead and draw that on the piece of paper over here, just so we can look at those differences. And I'll bring the numbers with me. Okay. So the black will be that'll be the vicarious hypothesis. That's the right spot. Blue is using the circle. And red will be the ellipse of chapter 47. So here's what I don't think you can see that color well enough. Sorry, there's circle. The circle says that it moves in too far here, so the circle has it go too slow in this region. Using this ellipse, it goes too fast in the middle longitudes. So Kepler's got the hunch that this ellipse is perhaps too elliptical. It's pulled in too far from the sides because it's making the planet move too fast in the middle. And then this number, which you should, this is the number to write down and meditate on, is that when Kepler made this ellipse, he pulled it in from the sides of the circle by an amount of 858. That's how far the ellipse came in from the circle. And now it's making it go too fast in the middle. And by almost exactly the same amount that the circle, using a circle with area time, made it go too slow in the middle longitudes. So the circle's too slow by about the same amount that the ellipse is too fast. And this is the amount that the ellipse comes in on the sides. So, so he that's where that goes. He says, well, using an ellipse is sort of cheating. Then he does what's just absolutely this is definitely the most difficult and painful chapter to go through what Kepler does in chapter 48. In this chapter, he says, I'm not going to do any approximations. I'm going to, for each and every single degree that the planet moves, I know how far away it is, I figure out how far it must have moved during that time. He works out the path of the orbit. It's a painful bunch of calculations, and it requires guessing what the total path, what the total circumference of the oval is. He doesn't know what that is. He makes a guess. He tries out making it move that way, and then maybe it moves too far, so he's got to try the whole thing all over again. Super difficult. He says, he's got this great quote. He says, I can't imagine anyone reading this not being overcome by the tedium of it, even in the reading. So the reader may well judge how much vexation we, my calculator and I, derived hence, as we thrice followed this method through the 180 degrees of anomaly, changing the eccentricity each time. So it's just, you can click, there's an Excel spreadsheet that goes through all the calculations. You can take a look at how that's happening. This is the shape of the orbit that it produces. So if you can see that, it's it's sort of an odd shape. It's not an ellipse. Doesn't really look like an egg. It's just it's a new shape. Whatever this shape is, if we want to give it a name, no one ever saw this shape before Kepler. He's the first person to ever see this shape. So, he tried it out to see if it worked, and it's better. It's better. I don't know if you can see these numbers here, but using this technique, it's now pretty much right on at the quadrant. It's off by 1 minute. That's fine. And then at the octants, it's a little bit too slow at the mean anomaly. I mean, at 45, it's behind. At 135, it's ahead. So once again, it's going too fast in the middle longitudes. So, this is suggesting something, that if it keeps going too fast at the middle longitudes, maybe his first hypothesis isn't right, and second, he specifically is bringing it too far in, and he shouldn't bring it in so much. But he doesn't give up yet. He says it's possible that I didn't actually accomplish what I set out to with this epicycle thing. So in chapter 49, he takes a very different approach. He's able to separate. Let's take a look at the picture here. He separates out the motion of the epicycle and the power of the sun. In chapter 49, he says the center of the epicycle will move faster when the planet is nearer to the sun. And the center of the epicycle will move slower when the planet's farther from the sun. So the planet doesn't actually move faster and slower based on its distance from the sun anymore. Now the center of the epicycle does. And you can imagine Kepler probably feels a little bit silly doing these things because he doesn't really, I don't think he believes that there's really a planetary soul moving it on an epicycle. But that's what he tries out. Let me click this. The YouTube viewers can see it clearly. Now, as you notice, this is the opposite of the shape in Chapter 46. Now the egg has got the pointy tip up top. In Chapter 46, the pointy tip was at the bottom. So it's another one of Kepler's eggs. So he tries it out, and it doesn't work again. Once again, if you can see these numbers here, it's too slow up at the top octant. It's right on at the quadrant, and down at the lower octant, it's ahead, which means once again it's moving too fast in the middle longitudes. And once again it's moving too fast in basically the exact same way that the circle moved too slow. So that's suggesting something again to him. Now the last thing is so chapter 50 is a very difficult. He sort of expresses in very short form, very briefly, a few other approaches that he tries to implementing this hypothesis, and none of them work. So basically, he ends chapter 50. Let me read the ending of this one. Actually, first, sorry, one other thing in chapter 50. He says there's a couple of very interesting things. One of them is that he says that he says on page 499 to 500, he writes, you will note again that what was observed in chapter 47, which was the ellipse, was that the truth lies between these two methods, the latter of which describes a perfect circle, and the former an oval, following the opinion of chapter 45. Therefore, you can at least conclude now, as well as before in chapter 47, that the lunules to be cut off from the perfect circle should have only half the breadth of the one that follows from the opinion of chapter 48. Well, what is half of that amount? All right, 858 divided by 2, 429. So Kepler is going to be thinking of some way of bringing the planet in 429 from the sides, where the radius is 100,000. And if he had any physical hypothesis that would do that, he'd be very happy. But right now he's got a vague hunch, not a vague hunch, but he's got a good hunch that somewhere between the circle and this ellipse that he pulled too far in, the truth must lie somewhere in the middle. And the width of this hypothesis of chapter 45, of using this rotating epicycle, that brings it in 858. So as a general thought, he believes that that it must be that the planet must be actually coming in by an amount of 429. So that's and that's it. That's where we're left by the end of chapter 50. So we've had, a hypothesis in chapter 45 with this epicycle, and we had him try it out in a bunch of different ways in chapter 46, where he gave up and used the vicarious hypothesis, in 47, where he used an ellipse, in 48, where he did it degree by degree, and then in 49, where he separated out the planet from the center of the epicycle, and then in 50, where he tries a few other ideas, but frankly, I found it very hard to follow what exactly he did in chapter 50. But the conclusion of all of it is that this hypothesis he had of the constantly moving epicycle makes the planet come in twice as far as it ought to. And that's where he leaves things then. So remember, one of those, look over the homeworks for these chapters. The questions include writing a summary of the epicycle hypothesis. We did the aside together, so writing out how much the ellipse differs from the vicarious hypothesis in chapter 47. That's just finding the numbers in the chapter. And then there's this one question. On page 500, Kepler writes that the lunule must be half that amount. How wide was the lunule in chapter 47? Well, it was 858. How much is half that number? 429. Write that number on a sticky note and put it on your bathroom mirror, a bathroom mirror at your office, too. I'd also suggest you write it on a piece of paper and put it on your pillow in the morning, so when you go to sleep at night, every night you see this number, 429. Because this number was in Kepler's mind for months. 429, 429, 429. What would make the planet come in by an amount of about 429? So, yeah. Okay, well that's what I've got as far as an overview of these ones. Do you guys have some questions from reading, either on these chapters or on earlier things? Let's see if there's anything about this first, and then also just general discussion too. Any thoughts or questions about these chapters in particular? I can still hear you. Oh. Just realized that's backwards. And I don't know why. There we go. Anything from past chapters?
Yeah. Yeah, I got a question from past chapters.
Okay. Go for it.
So, I used the law of tangents for the chapter 19 worksheet, and I managed to get the angle CSM, which we were looking for. I don't know how to find that angle in relation to the zodiacs, to the position on the zodiac. Anyway, that was the last part where I got stuck.
Let me take a look at that. CSM.
I didn't notice the what Ben had drawn up for us as the worksheet inside of the book. I mean, unless it was in chapter 16, but I didn't look that closely in it.
Yeah, I think it was. I'm taking let's take a look at this. Just pulling up the homework now. Okay, the assignments. Chapter 19 worksheet. Is this worksheet 1 or 2?
It's the one on the latitude. I don't know which one it is.
Let's have a look here.
Jenny says it's number 2, she thinks.
CSM. Okay. Let me put that up on the screen for everybody. Okay. Is this the one?
Yeah, that one.
Okay.
I'm gonna go grab my work. I'll be right back. Okay, sorry.
No problem. I'm just going to put it on the screen behind us here. Hmm. Okay. Okay, great. So so let's go through this, and then you tell me. Let's go through where you're at on it. So I'm going to draw it up on this paper here. So we got 49, 15, 37. Now is this facing? You can see this. The numbers are facing the right way now, right?
Yeah, they were facing the right way on the, the whatever the connected share screen, but on the screen behind you it was backwards. But
Okay.
the share screen was fine the whole time.
Okay. Got the center, got the sun, got Mars, got the equant. We got a bisected eccentricity, which means that both of these distances are 9282. And we have what's the name of this angle up here, Anastasia?
Where the equant sees Mars?
Yeah.
I don't know.
Anybody help her out there?
Mean anomaly?
Say again?
The mean anomaly?
Yep, mean anomaly. Okay. Oh, we know that this is the radius. Right down. So how did you approach this one, Anastasia? What did you do?
I did a lot of things. But the one that got me somewhere, so I first found out what that angle MEC was.
Okay.
And I did that by subtracting 49 degrees, 15 minutes, 37 seconds from 180.
Okay.
I got 130 degrees, 44 minutes, 23 seconds.
Say it one more time, will you?
130 degrees, 44 minutes, 23 seconds.
Okay, looks right.
Okay. And Then I used the law of sines.
Mm-hmm.
So I just did the relationship of the sine of 130 degrees, 44 minutes, 23 seconds, over 100,000 equals the sine of EMC, over 9,282.
Okay.
Forgot my page, which I did all my work on, but I can
I'm
pull.
just gonna.
There you go.
Like, this is a great calc. You can get these calculators. These are not much money, but they're so handy because you can type 130 degrees, 44 minutes, 23. Oops. Seconds. I know it looks like a minute sign each time, but it, I mean a degree sign, but it knows it means you mean minutes and seconds. And it's so convenient. You can get that. Okay. So what do we get? 0.75. So take that number, multiply it by 9282, and divide by 100,000. Right. And then, so then another great thing about just like having a calculator is you don't need a fancy computer. This calculator is fine. So now I got this number of 0.07.
Mm-hmm.
And then to do the inverse sine, I have to push this second button, and there's this sign with a -1. I can't see that, but I'm going to say, what's the inverse sine of that last answer I had? Equals. And that gives me the degrees. And I can push this degree, minute, second button, and it turns into degrees and minutes and seconds, which is really handy. $9. Okay. So 4150. Is that what you got, Anastasia?
Let me pull it. I took a picture of it. Let me.
Okay.
Yeah, I got 4 degrees, 1 minute, 58 seconds.
Great. All right. Then what'd you do?
Then I was able to find what that angle ECM is, which is 45 degrees, 13 minutes, 49 seconds. And I did that because every triangle is made up of 180 degrees. So you add 130 degrees, 44 minutes, 23 seconds, plus 4 degrees, 1 minute, 58 seconds. Subtract that from 180, and that gives you angle ECM.
And you got?
Maybe I did some math wrong, but I got 10 more seconds than that.
Oh, yeah, whatever. That's not a big deal.
Okay, so finding that angle, you're able to find the angle MCS.
Because it's 180 different from it, right?
Exactly. Yep. So we subtract 145 degrees, 13 minutes, 48 seconds from 180, and that gave me 134 degrees, 46 minutes, 11 seconds. Well, if I did the math wrong, then it'd be a little bit different on there.
Well, just from this number, it would be 12 seconds, because 12 and 48 make 60.
Okay.
I'm going to say 20. Well, okay, all right. I'm going to put 12. Okay.
Okay. And this is where it was the most frustrating part. I was stuck on it for a long time. But I didn't know what tangents was.
I'm just going to redraw with just that one triangle.
Okay.
Clear things up for us. Okay. And then you did the law of tangents, huh?
Then I did the law of tangents.
Ugh.
Because we don't know what angle CSM is or angle CMS.
Right.
It's the law of sines. So I don't know if we want to write out what the law of tangents is, but
You know, can we actually do the law of cosines instead?
sure. I don't know what that is either, but
It's just, the law of tangents just stinks. And let's this is the law of cosines. I guess I'll write just the formula itself on a separate sheet here. Okay, so we'll come back to this question in just a second.
Okay.
But in general, for any triangle, so c squared equals a squared plus b squared minus 2ab cosine angle C. That might not look any nicer, but it's well, maybe it isn't any nice. Well, I'll tell you. How about we try using this to solve this triangle and see what you think afterwards. See if you're sold on using it instead of the law of tangents.
okay. We'll determine how much hair I pull out. That'll be our.
All right. Make sure you're counting. Here's our thing here. So for our triangle, we want to know what MS is. This is the unknown. Well, basically what we're going to do is we're going to find this side and then use the law of sines. So yeah, it involves one more step. Maybe that seems like kind of a, but it's just let's just go ahead and do it and see what we think here. So for us, MS is like that side C that we don't know. So we can write MS squared equals 100,000 squared plus the other side squared minus 2 times 100,000 times 9282 times the cosine of 134.4612. So MS squared equals, and then you can basically put all those things right at once into a calculator.
So 100,000 squared plus 9282 squared minus 2 times 100,000 times 9282 times cosine of 134, 46, 12. Some big number. I'll take the square root of that answer. There's my number, 106,000, that's a comma, 106,740. Or I guess 741 if we went around. 106,741. Yep, wrote that right on top. That's not very nice. And then, we're going for this angle down here. So then we'd have the sine of the unknown angle, CSM, over its opposite side, 100,000, equals the sine of 134, 46, 12, whatever, over 106, 741.
I like this plan.
So I'll go ahead and do the right-hand side of this. So I take the sine of 134, 46, 12. I divide it by 106, 741. Multiply it by 100,000. Uh-oh.
You're supposed to multiply it first, I think.
No, he.
Try that again. Sine
Yeah.
134, 46, 12. Oops. Times 100,000 divided by 106, 741. Okay. So there is 0.665 is the sine of CSM. So then I push my inverse sine of the answer. Get that many degrees. Push my degree minute second. So 41, 41, 25. This says.
That's basically what I got. We're like 1 second off.
Oh, great. So, what's your, how much hair did you pull out?
Well, Jenny claimed to have pulled out less hair. She likes this.
Okay, good. Whose hair did she pull out?
She pulled out so much hair with the law of tangents. It's ridiculous.
No, the law of tangents, it's really bad. I mean, I think it uses it, there's like less actual steps involved, but if you've got a calculator, it's just more convenient using the law of cosines. The law of tangents is just a little bit strange. I don't know. Just my take on it. So then that would be, so then now let's compare that. Hey, look, let's go ahead and take a look. So what is that number we got there? Let's look at it again. We got 41, 41, 25. 41, 41, 25. So let's take a look in chapter 19 and see if that's what Kepler got. Where is this? Let's see. Um, hmm. Well, I'm having some difficulty finding where this is here. What was the second part of your question, Anastasia, on this?
Well, because I couldn't find it, I assumed that maybe the problem was that I needed to convert it into its position on the zodiac.
Oh, yeah, yeah. For that, you need the aphelion, which... Where did the... let's look back at that chapter. So this had those numbers at the end. I wonder where they came from. Oh. You know, we can do this. We can look at... let's look in... Here we go. Let's take a look at chapter 18, is where he's got the... yeah, this is what we can do, is we can look in chapter 8. Let's figure out the example Ben was taking that from. At the table in chapter 18, he says what these mean longitudes are for these different observations. And remember, you had a... What did we... For this homework question, we had a mean anomaly of 49, 15, 37. So let's look for which one of these observations has a mean longitude of where is this here? 49. Oh yeah, it's the observation of 1582. So let's take a look. Let me put this page up on the screen here, actually. If I can remember where I put. I do not know where I put that. Oh man. Well, shoot, I don't know where I put it. So, here, I'll hold it up under the camera. Oh gosh, it is small print. You probably can't see that right there.
No, it just looks like I have it in front of me.
Well, you know, if you got the book, you can at least look in the right spot. So in 1582, he says, well, first off, he says, what's the aphelion? Well, since you can't see this, I'll just sit down anyway. You know, just to, if everybody takes a look at that on page 277, you know, Kepler says, okay, what's the aphelion in 1587? That's the first row. And then he says motion over the intervening years. That's how far did the aphelion move. You know, the aphelion moves every year, so he's got to adjust that for what year the observation is from. So then he says, okay, so here's the aphelion in the year 1582. The mean longitude was when was the planet seen. This next line where he says add 3 minutes 55 seconds, that's one of the two things he found out in the vicarious hypothesis. So the first mean longitude, that just comes back from the table of that's the number Tycho would have given. In the table at the end of in the table in chapter 15 for the observation in 1582, the mean longitude is 3, 9, 24, 55. 3 signs, 9 degrees, 24 minutes, 55 seconds. And that's exactly what Kepler has here. 1582, the mean longitude is 3 signs, 9 degrees, 24 minutes, 55 seconds. Then he says add 3 minutes, 55 seconds. You notice that on every year he keeps saying add 3 minutes, 55 seconds. Do you know why that is or what that means? Why is he doing that?
Well, that has to have been the adjustment for what he made for going from the mean sun to the parent sun. Is that what that is?
Sort of, indirectly, right?
Okay.
Pretty indirectly. Well,
Is it the precession of the equinoxes?
well, it's the same for every year, so no. The precession of the equinoxes is incorporated into the. I think that's incorporated into where he says the aphelion is. Because that includes both the precessions, I think 51 seconds a year, and the actual motion of aphelion, I think, is 23 seconds. So you put it together and you get 1 minute and 14 seconds, something like that. That's the total motion of the aphelion compared to Aries, the fixed compared to the first star of Aries every year. But that's not so that's taken care of in the second row. This one where it's 3 minutes 55 seconds for every observation. Let me ask you this: what does the mean longitude mean for Tycho? What does that mean? How would he write down in his table what the mean longitude was? What is the mean longitude anyway?
It's just the average time of the planet on the eccentric.
Well, that's how fast it changes. But what else? You see, if you go back to let's put this animation up of the vicarious hypothesis, because again, there's two things that Kepler plays with in there's two free variables in the vicarious hypothesis. So in this animation represents changing the two of them. Drawing the 4 circles and seeing if they all have the same center, that's not quite what Kepler did, but it's close. But the two adjustments made are exactly what Kepler did. Moving the mouse horizontally, move the mouse horizontally. See where the blue, the equant's moving? The direction of it from the sun is moving around?
Yeah.
That's changing the line of apsides. We say, who knows what the line of apsides is? Well, let's figure it out. Here's the other thing. If I move the mouse vertically, I'll move it all the way to the left there. Look what happens there. What's going on with that? The line of apsides isn't changing. What's changing right now?
The
Centers. The centers.
Well, their result. What's causing them to change? What's the one thing that's changing with my?
What it's seeing, where it's seeing Mars.
Where the equant seeing the angles from the equant, right? The angles from the blue point, they're not changing. Let's do it with 3 points just to make it a little bit, well, whatever. Right, the relative angles don't change. We know based on our clock moving at tick-tock, tick-tock, it moves around once every 686 days. We know, how far the clock hands would be between 2 times it saw Mars. But we don't know we have to set the clock.
Oh.
So Tycho had an idea of what noon was. Kepler's got to set the clock. So he said is take what Tycho said the mean longitude was and add 3 minutes and 55 seconds. Got to add the 3 minutes and 55 seconds. Those are the two things that make up the vicarious hypothesis. Those are the two things that Kepler's free to adjust. Where's the line of apsides, and what's the mean longitude supposed to be? How do I set the clock of the equant? So what Kepler ended up finding out was, he said, well, where's the aphelion? And he said in 1587 it's Leo 28, 48, 55. That's it. That's the aphelion. And the amount you got to reset the clock compared to when Tycho set it is 3 minutes and 55 seconds. So that's the reason for that row.
Okay.
Where it says add. That's why he's adding that. To look back to where that came up in, he says it on page. I'll show this up to the camera. This is on page 268. Again, this might just help you find it on the page. It's probably not legible. It says, well, anyway, this is when he's going through all those bajillion, let's glance at this. So he's got all these different attempts for the vicarious hypothesis. And he concludes. He says, therefore, the total addition to Tycho's longitude is 3 minutes, 55 seconds. And the aphelion is placed at 28, 48, 55 Leo. That's his conclusion. So those are the two adjustments he's been making to get the vicarious hypothesis. Once he does that, he then calculates what the eccentricities are from it. The eccentricity of the eccentric, sun to center, is 11,332. Eccentricity of the equant, 7232. So I think the focus is, let me change the focusing on that. You probably still can't read it, but at least it's focused. Well, yeah, probably still can't. Yeah, it's just not locking onto it. Anyway, he's saying, that's where that comes from. So, okay, so then going back to the question we had here. So we had gotten 41, 41, 25. Let's take a look at what Kepler has in that column there. 1582, so where's the aphelion, blah, blah, blah. What's the mean longitude? Add 355 to it. Here's the corrected mean longitude. 3 signs, 9 degrees, 28, 50. He says, therefore, what's the angle C? Now, mean longitude is not an anomaly. The mean longitude is where in the zodiac does the equant see Mars. The mean longitude, he writes it as just 3 signs, but when he writes 3 signs, that means it's Cancer.
So do the zodiacs have specific numbers? I was trying to...
Yeah, if you take a... switch over to the camera again here. I mean, here's the order of the zodiac. Focusing thing. So this is 0, 0, 0, 0, 0, beginning of Aries. Oh, you can still see it down here, right?
It stopped. No.
There we go. So Aries is the beginning. This is it. This is 0. So when Kepler says that where is aphelion, he says, if you notice the first column he writes Leo. Then after that he writes 4. 4 signs. 1 sign, 2 sign, 3 signs, 4 signs. Now we're into Leo. So sign means 30 degrees. It means jump ahead 1 sign. So the aphelion is 4 signs, 28 minutes. That means 1, 2, 3, 4 signs plus 28 minutes. So at the end of Leo over here. The mean longitude, he says, for that year is 3, 9, 28, 50. So 3 signs, 1, 2, 3 signs, 9 degrees. So over here in Cancer. Meaning the equant sees the planet in Cancer. and aphelion is over here in Leo.
Okay.
Let's just write down those two numbers then. So here's the aphelion, and here's the mean longitude. So aphelion. To write down the numbers, he says the mean, the aphelion is 4, 28, 44, 27. 4 sines, 28 degrees, 44 minutes, 27 seconds. And the mean longitude is 3 sines, 9 degrees, 28 minutes, 50 seconds. So to find the difference between them, each sine is 120 degrees. I mean 30 degrees. So 4 sines is 120 degrees plus these 28. So it's like 148 degrees. 44, 27. This, we've got 3 sines, that makes 90 degrees, plus the 9 makes 99 degrees, 28, 50. So the difference between aphelion and longitude, that's what's called an anomaly. So the difference between them, the difference between, uh-oh, this is not that 45 degrees. Oh, I mean 49, wait a minute. I think I switched to the wrong example. What was the angle we were looking? Oh no, it was 49, 15, 37, right?
49, 15, 37.
So that's that 49, 15, 37. That was the this initial angle that we had in the very first sheet going through this. That's where this angle comes from. Between the aphelion and where the equant sees Mars. The aphelion's over here in Leo, 4 sines, 28 degrees, 44 minutes, 57 seconds. So if we were going to stick this on it properly, you have to tilt it like this. So the equant, so here's the aphelion. Where's Leo? The equant actually sees the planet over here in Cancer. So 49 degrees is the difference between them. So remember, so this is an anomaly. Mean anomaly. So the difference again, a longitude is like a direction in the zodiac. An anomaly is an angle of how far away we are from aphelion. An anomaly is within the orbit. A longitude is a general astronomical term. So, to finish off this one homework example, so Kepler says, therefore the angle at C, in that chapter it was C, not Ben put E on his homework, but therefore the angle at C is 49, 15, 37. Then he does this law of tangent stuff, and he gets the angle at A from the Sun, 41, 47, 23. What did we get?
41, 41, 25, 26.
Right. Right. And then what did I just say? 40. The other one was 41, 47, 23.
Yeah.
So 41, 47, 23. So the difference, 6 minutes. So the difference. Blue one is what you had in the homework. This is what the bisected eccentricity. This is the bisected version of the vicarious hypothesis. What Kepler did in the table we just read from in chapter 18, this is from the actual vicarious hypothesis. So we didn't get 8 minutes here, we got 6 minutes. But with that work that you did, was you got a number we could compare to see how far off is the vicarious hypothesis when we bisect the eccentricity, instead of using the real numbers that Kepler originally found. So, it might have been nice if the homework example got the 8 minutes instead of 6 minutes, So you get, I got the 8 minutes, but 6 isn't, 6 is pretty close.
Okay.
Is that just because some of the decimal places on the signs and things were just not as accurate or something?
No, it's just because that's not where it's as big. I think if it was at one of the ones where it's 135, we'd get a bigger difference. To look at the example, the specific example where Kepler got the 8 minutes was in Oh wait, that is the one from 1582. Yeah, well, I'll be damned.
So it's going towards perihelion?
Cancer. Mars falls at 17. 7. We got 41, 41. Just a second here. 6 minutes. So we would have 17. Yeah, I don't know where Kepler got that number from. Because he says that. Yeah, he says that with it bisect, we would have gotten 17, 4 3/4 minutes cancer. But I think with the number that we just got, we would have 17, 3 cancer. So it really is more like 6 minutes and not 8 minutes. Huh. Wow. So either we both independently got the wrong number on this, even though you used the law of tangents and we did the law of cosines here, or Kepler made a mistake and the 8 minutes was slightly smaller. Uh-oh. Now, I'm amazed the translator didn't add a footnote about this, because he likes to point out when Kepler makes mistakes. But yeah, I don't know. I don't know what to say about that. It would be 8 minutes off from the observation.
You mean what we have would be 8 minutes off from what was actually observed?
Well, he says the value differs by 7 2/3 minutes. According to the calculation we just did, it was actually 6 minutes. The vicarious hypothesis is off by about a minute in that year. It's off by a minute and a half from the observation. So our difference would have been 6 minutes, but the vicarious hypothesis was also off by a minute and a half. So the total difference between what we just got and the observation would be 7.5 minutes. Guess you better send that homework in to Ben and see what he's got to say about that.
Okay.
Yeah, because yeah. All right. Well, the 6 minutes of Kepler.
You can ask me
why, buddy.
6 minutes. Why the 6 minutes? Why the 6 minutes?
Okay.
Well, that was really useful. Thanks.
Yeah, sure. Yeah, good. No, it's great. It's because you have to actually get in and do that stuff. So sure, good. Anything else? Just make sure that whoever's on YouTube didn't leave a comment or a question.
Oh, I got a text from Ray. Did you get a text from Ray?
Oh, I got a text during this, but I didn't look at it because,
He wanted to ask a question.
Oh.
Because what does luneal mean?
Oh, it means a little moon. It's pull up that picture. Yeah, it's not a scientific term. It just means a loon, like Luna is just moon, and a lunule is a little moonish shaped thing. So there is, so this is the lunule here. It's called that because it looks like, like a part of a moon.
Hey, Jason?
Yeah.
You were saying that mean longitude is what we would call an epoch today, right?
Setting the mean longitude would be called the epoch. Yeah.
Setting it, okay. Yeah, like where it physically is at a certain time and date in space, in reality.
Yeah, like today, the parameters of an orbit are how big is the orbit, how eccentric is the orbit, how tilted is the orbit, where is that tilt, where are the nodes, where is the line of apsides, that tells you where aphelion is, and then you just need one more thing, which is where's the planet. So you say, on this day, here's how far away it was from. Today they use perihelion instead of aphelion. So on this day it was this far away from perihelion. So the epoch today is this is the mean longitude on the January 1st, 2000.
Right. Okay. So setting the mean longitude is the same as the epoch.
Right. Yeah.
Okay.
Yes. In other words, having the mean, having the standard that you would then say what your mean longitude is based on how many days have passed from a certain date. Well, when was that date that it would have been like right at zero? Figuring out when that date was is the that's like the epoch. That's like the correction that Kepler made to figure it out. When was. It comes from also changing the line of apsides, so it would definitely be different from Tycho because already where he's putting the equant is different, so you'd expect it to change some.
Okay. Yeah.
So that's why when I said to Anastasia that it's sort of partly due to using the apparent sun instead of the mean sun, it's because that's that is why he had to add that amount because his model was different from Tycho is because he used the apparent sun. But the more specific reason was that that's the number that he got when he made the vicarious hypothesis work best.
Gotcha.
There's another one here. Okay. Someone wrote in about how Kepler makes them pull out their hair.
No.
I said pulled out their hair with Kepler's 6 minutes. Anyway.
Was that Ben?
No. I don't know who this person is. Hi, person. For your comment.
I think it's unanimous.
Yeah. Well, anyway, but now we can all save our hair by using the law of cosines. Yeah. Well, if you look at these pictures of Kepler, I think he has hair, so, maybe he was using the law of cosines also. Anyway.
Well, he also did have another person doing all the calculations for him, right?
Well, sometimes he had some help. Not all. He does have a bit of a receding hairline. Compares earlier. Yeah, probably from the law of tangents. Even as a young man, it comes forward. Yeah. Okay. Well, maybe I guess we ought to get going before the thing anyway. Unless there's any other questions? So can anyone, just to review, between the mean longitude versus the mean anomaly, what's the difference between those two? What do those words mean?
I guess the mean anomaly used to mean the angle from the equant, but I guess now it means it's the angle from the center without the equant. Is that right?
Well, the angle from, there's a couple things that might mean. The angle from the equant. Could you say a little bit more about what you mean there?
Well, from the equant to the planet, that's how much it sweeps out. That's the mean anomaly, right?
What's the mean longitude? Let's start with that one. I mean, it sounds that's right, but it might not. It's not. It's just not precise. Quite what I'm. Well, how does it differ from the mean longitude? Let's put it that way.
I guess the mean longitude. Actually, I don't know. I mean, I know what longitude is. Like that's just the position of the planet on a flat plane. I guess you could say, not on the latitude, but it's a longitude.
Mm-hmm.
I'm not sure how it would be a mean longitude, so I don't know. But that's.
Well, it's important when you said it's the position of the planet on that plane. How do we, if you're just going to make up some number or some possible thing Kepler might write down, and the mean longitude is, or the planet's longitude is, what might he write after that? Like Mars's longitude was blank. Make up. How might he finish that sentence? You just make whatever the number. Just make anything up. What might he say?
50 degrees.
Well, it would have to be in the constellation.
Yes. Yeah. Kepler wouldn't say the mean longitude. He wouldn't say the planet's longitude is 50 degrees. He wouldn't
Right.
say that.
50 degrees no, he would say. You would not have 50 degrees. It'd be 30 degrees Aries or whatever.
Yeah, 20 degrees Aries. Yeah, he might say the longitude is 20 degrees Aries. He might finish a sentence. The mean anomaly was 50 degrees, or the mean anomaly, or the eccentric anomaly is 50 degrees. The equated anomaly is 50 degrees. The apparent anomaly, which is the equated, yeah, he would say those things that way. So, yeah, anomalies are in degrees. Longitudes they're in the zodiac. They're expressed in terms of, Aries or whatever. Usually the mean ones, they don't say the name of the constellation. They'll write a number for it instead. I'm not sure quite why that's the practice, but that's how it goes. So they might say the mean longitude is 4 signs, 20 degrees, blah blah blah.
So how does that mean? Is that just instead of just saying the name of the zodiac, they just have a number? Or is this...
Oh well, it's because it's where the equant sees the planet. That's what makes it mean.
Oh.
So the apparent longitude, in this vicarious hypothesis animation, the blues and the red things there. Let me just scroll down here. The things that he starts with, these are longitudes, right? So these are apparent longitudes. This is where the sun saw Mars, and these are the mean longitudes based on Tycho's way of setting the clock. These are all actual directions. Well, because he twists them, maybe that's why he just calls them in terms of signs and things instead of a specific zodiac direction. But the mean longitude, after he's got the vicarious hypothesis, is an actually, I forgot what I was going to say now. Or how... Oh yeah. Anyway, so the mean longitude. So here, here's the vicarious hypothesis. So this angle HCF, that's the mean anomaly. HAG, that's the apparent anomaly or the equated anomaly. You can't, with this diagram, you can't say what a longitude is because we don't know where Aries is. So once you have these diagrams like this, you're basically dealing with anomalies. When you're using observations, then you've got longitudes.
Right.
You can only draw this diagram if you know where the line of apsides is. Well, if you have a line of apsides, anomalies are how many degrees are we from the aphelion. Longitude just means that's the, I saw it in Aquarius or whatever. The mean longitude would be where did the equant see it, if the equant actually existed and it watched it and then it saw a constellation behind it. Which one would it be?
Right.
Thanks for the comments, YouTuber. I'll make sure to add, in case I forgot, but I'm pretty sure the what's it called? The video description here. Let's see if it includes it. Yeah, the readings and the homeworks for anyone else who's also joining us online. The readings and the homeworks are in the they're linked in the YouTube description there. As far as getting a copy of the book, I suggest interlibrary loan. They're very rare, and if you try to actually buy a copy of the New Astronomy, it costs a fortune. So. Okay. Any other quickies before we wrap it up for today? And remember, this goes for everybody. You know what? We can set up private hangouts once a week. I'd really like to.
Yeah, I'd like to plan on one for Sunday, Jason.
I feel like we just had one today, actually.
Yeah, I see LA and San Francisco on, but I see no people.
Well, that'll do it for the YouTube stream tonight, and we'll see you again next week.